status. He has contributed very influential work and very relevant to this workshop, in particular by laying the foundations of algebraic signal processing, which have been instrumental, I believe, to the development of GSP, this field that we are here discussing. He's an IEEE fellow. He received the main student teaching awards at both CNU and DEGAS. His long-standing research interests include problem generation, board performance, and novel forms of Fourier analysis and signal processing. And a recent focus on machine learning as well, as most of us, I guess. Today, he will talk about the Fourier analysis on directed graphs. So again, please join me in welcoming Markus.
So good morning, everybody. Thanks for the introduction, and particular thanks for inviting me. I'm very happy to be here, just like everybody post-COVID. Being actually physically present somewhere and talking to real people is a real pleasure. So the topic of the talk is direction in the signal domain in various forms, and you will see what I mean by this. But first, I want to give a little bit of context that he mentioned already, that you understand where this work comes from, and also what is my kind of thinking in presenting the work. So the context is, it was mentioned, the algebraic signal processing theory. I was working a while ago on this together with my collaborator, Jose Moura, and then later some others. And it started as a theory to understand fast transform algorithms. That's the part on the right, but then evolved into a general theory to generalize signal processing to new signal domains. So go beyond discrete time signal processing, and that's the part on the left. And the generalization is done using abstract algebra. There are other ways of doing it. Recently, we see topology, but this is one way of doing it. Since I have here a reasonably nice audience, and I'm curious, who has ever looked at any one of those papers that you see here? Just saying, okay, good. Okay, that's much better than expected. For the rest of you, that's your homework, of course, right? So, yeah, so let me just summarize. It's a little bit abstract, but I still want to understand where I'm coming from. There's some insight. The theory is very general, and it provides many insights in what's really going on in signal processing. One aspect of it is axiomatic. So what do you actually need to get a meaningful notion of signal processing? And what you mean is these three things. Most importantly, you need a filter space and a signal space that satisfy certain properties, and people in algebra call them algebra in module. Okay, it just captures the basics that you need. And it turns out that once you have that, everything you need for signal processing is defined. So you can derive what's convolution, what's Fourier transform, and so forth. Of course, sometimes it may not exist. So the math just tells you it doesn't exist, sorry. But sometimes it exists, and then you get a framework. Now, the question is, where do these signal models come from? You can invent infinitely many, and most, of course, don't make sense for applications. And one of the insights, the key insight maybe, was that you can derive them from just one single object, which is the shift. So you define a shift that you find meaningful, and then you get the signal model automatically, practically. There's no creativity, and then you get your notion of Fourier transform and everything, and you can use it to do signal processing. So the shift is everything. Okay, that was one thing. And there's some other insights. For example, shift invariance just corresponds to the algebras being commutative, which means they consist of polynomials. And also one particular interesting insight, these boundary conditions that we use, like periodic, and for the DCT symmetric, and so forth, you get a very detailed insight why these boundary conditions are not others. Okay, that will be relevant later. So just one more slide on this. So back then we investigated discrete time signal processing, and then of course with the insight, the shift is everything, we started to look into just change the shift, right? And the first idea was do a symmetric shift. What you get then is in GSP terms, a undirected path graph, the Fourier transform becomes the DCT. And the paper called 1D Space was the first paper actually to change the shift. And of course, it was flat out rejected because reviewers said, like, why would you change the shift, right? It's such a weird thing, right? What does that even mean? But in the end, it got through with some, got better, also more understandable. And then we had some more generic shift. That's a path graph with arbitrary weights. In all these cases, you get FFTs. So that was nice. What other shifts can you dream of? Back then, what I could think of are these. You could do 2D non-separable signal processing. And here you see the shifts a bit visualized. Now you have suddenly need 2 shifts to get this working. And again, you can derive the boundary conditions, you can get the FFTs that go with it, and you have a complete signal processing framework. Of course, these grids maybe are not the most popular one, but they're pretty, and they have occurred occasionally in signal processing. Now, of course, we are here about graphs. And Jose in 2005-06 already had the great foresight to say we should do graph signal processing. And I kept insisting that I don't think that makes sense. And that was maybe the not a highlight in my career to say something like this. But I looked a little bit into this. In this archive version, you find a little sketch how to go about it. You take a weighted graph that gives you a matrix, and then you take this as a shift, you derive the signal model, and if minimal polynomial and characteristic polynomial are equal, you get a meaningful spectrum and so forth. The reason actually why I thought it doesn't make sense is because I saw no way to get an FFT. At least there, I think I was right. So we are stuck with graphs up to 5,000 maybe, and the 1 millions that the machine learning people like, they're sort of out of reach. Important here is another little insight, which is not particularly deep, but if you do signal processing with 1 shift in the discrete finite dimensional case, it's equivalent to GSP, okay? GSP has 1 shift, and if you start with 1 shift and the shift is linear, it will correspond to a matrix and that will define a graph. So 1 shift is GSP. Okay, meaning you want to do something different, you have to need more shifts. Okay, so that's my kind of thinking in the work that comes. And I have 2 parts. The first part is so I consider the warm-up, even though you may find it, of course, also hopefully really interesting. But it's a warm-up, and the bigger part is part 2, where I show a new way of doing signal processing different from GSP. So one topic after getting back to the business of graph signal processing, we saw that directed graphs are a bit of a problem. And let's talk about this. So we know that for undirected graphs, this GSP works beautifully well. So you can take the adjacency or the Laplacian, whatever is your favorite, but they are symmetric. So you get an eigenbasis that exists, and it's even orthogonal. So you have energy preservation and so forth. So it's really nice. For directed graphs, it gets tricky because whatever you use as the shift, it is not symmetric. So it's not only that the FFT is not orthogonal, it may not even exist at all in general. So you must be lucky actually so that it exists. And I think a notorious example is the simplest graph you can come up with a directed path graph. You see that here on the left. If you look at the adjacency matrix, it has only 1 eigenvalue 0 4 times. And also the Laplacian is not much better. It has 1 eigenvalue 1. So it's a Jordan block. It's the worst case. There's no eigendecomposition whatsoever. In fact, there's no invariant subspace whatsoever. So you're completely as far away as possible from having a Fourier base. Okay, so that's kind of a worst case. And many people have addressed this problem. Here I collect all the papers we could find, and they all have their pluses and minuses. So there's no perfect solution where you look at it and say, yeah, that's the solution. They all have like some advantages and some disadvantages. It could be maybe it's not as elegant. Maybe it imposes something that is a bit unusual. It changes the total variation definition in some way, or it may not be scalable beyond graphs of size 100. So, I mean, you are to judge, right? But it's really worth studying them. So what we did is we add another method, and then you can look at it whether you like it. The motivation is shown here. Imagine I give you a finite piece of a time signal, okay? And imagine you never took signals in systems, and you just know GSP. And then you would start like, okay, this is a time signal. Let's write down the graph. And this would be the natural graph that you see here. That's the graph. But we have just seen that GSP doesn't give you a Fourier basis. So you would be stuck right there. However, of course, we all took signals in systems. And if I tell you here's a finite piece of a time signal, compute the spectrum, you would use the DFT. Of course, right? First thing. Use the DFT. However, by using the DFT, you implicitly extend the signal periodically. And in graph terms, that's equivalent of adding this backward edge. So in essence, you make the domain a circle. Okay, like shown here. On the matrix, it means that you add 1 edge, and that gives you that 1 in the bottom corner. And it turns out that this matrix now can be beautifully diagonalized. And in fact, that edge that is added is the unique solution. Any other edge won't do it. It's this edge that you have to add. And now the key observation is this. We do this, and the signal is practically never periodic, right? It's a piece of a time signal. It's not periodic. It comes out of a piece of music. The edge is fake. Let's call it a fake edge. It's not in the data, but we live with it, okay? And that was the starting point, and it's very easy to understand what we are going to do. We ask ourselves, if I get now another directed graph like this one, a random one, can I do the same thing? This graph is chosen so that it's not diagonalizable. It has these two Jordan blocks. And we ask ourselves, can we now just add some edges to make it nice, right? To get a nice diagonalizable adjacency matrix. It turns out in this case, for example, these two edges will do. So you add also here fake edges that are not in the data, but then you have a Fourier basis just on the left side. And that was then in essence the goal. Given a directed graph, add a small number of these fake edges, so you have a nice Fourier basis, okay? Just like we are used to do every day when we apply DFT and assume periodicity, okay? That's the idea. So how do you go about something like this? Well, you look in the math literature, right? Because everything has been invented already in mathematics, almost. You look in math literature, the theory that helps you doing this is called perturbation theory. It studies when you have a matrix and you have eigenvalues, and now you make a low rank change, how the eigenvalues change. Now, and there are some theorems, there's not too much literature on this, but it turns out we make a specific low rank change. We add one edge, right? It's a matrix, all zeros and 1, 1. So it's a rank 1 matrix, and then maybe we add a few of those. And so we had to specialize this to our scenario and get sort of a corollary. And the corollary says that you're adding one edge, you can destroy the largest Jordan block, okay? And now the question is, how do you find this edge? And there we had also a theorem that in essence gives you an equation. If that is fulfilled, then the edge is a good one, okay? So it allows you to find the good edges to add. So here it's kind of depicted. Here's a matrix, there's the largest Jordan block, and you add that one edge, and then the largest is destroyed, and the others may still be there. Good, and now what you do is you do this iteratively, right? You keep adding edges until all the Jordan blocks are gone. There are lots of tricky details because one tricky thing is you cannot compute the Jordan normal form, right? It's not computable beyond 100. It's numerically unstable. MATLAB cannot do it. Maple, Mathematica is not computable for large sizes. So you have to apply some tricks to actually get this numerically done in MATLAB. But we did all this, and in essence implemented it in MATLAB. And yeah, that's sort of what we did. So this is just a sketch of the algorithm. And while we are adding edges anyway, we thought it may be nice to also destroy zero eigenvalues, because zero eigenvalues also make a problem in the adjacency matrix. So let's get rid of them as well by adding a few more edges. And doing so actually makes sure that what you get as a Fourier basis is numerically stable. Because the Fourier basis then you need to invert to get the Fourier transform, and the inversion has to be again computable, and that needs numerical stability. Good, so here's the example that I showed before. It turns out here you have two Jordan blocks, and then you get an equation, and the equation shows you this should be not equal to 0. That means you have a choice of 5 edges here. 5 edges will do the job, destroying the largest Jordan block. You add 1, then there's still 1 left. And then you get another equation. This time you have only 2 choices that are good. You pick one of them and it's gone. So that's the story. So what does this do to the eigenvalues? Well, let's look at the example before the time graph. If you go with this graph, it has only one eigenvalue 0. And then you put that backward edge and they kind of explode and they all move, as you know, of course, to the unit circle. So you see the change in the spectrum is considerable. And that's not any different in these graphs, right? So here's before, I have only 4 eigenvalues, and now you have a complete set of 7. Good. Now, there's more I can say about this. There's a paper, you can look at it. Just one thing we really wanted to make sure is it can be really used, okay? So we tried graphs. So we took 500 nodes and 5,000 edges, we use different graph models and we generate randomly for these graph models. And you see here's the minimum number of edges that needs to be added to fix the graph. Here's the maximum, here's the mean. So you see that in these two models, Barabasi, Albert, and Clem-Egiles, all the graphs need fixing. None of them has a Fourier basis to begin with. What Strogat sometimes has, okay? So there's nothing that needs to be done. But all these need fixing, and sort of in a few seconds, they get all fixed with few edges, okay? But then again, scalability is matters. So we looked at large graphs, 2 examples, just to see when does it break, because also the numerical stability may be problematic, but it turns out we get it very scalable. So 5,000 nodes, that's in GSP a quite decent size. And also here in minutes now, we could fix these graphs and get a meaningful Fourier basis. Good. Now, what about the Fourier basis that you then find? It turns out the Fourier basis, of course, will not be orthogonal, right? The graph is still directed, it's not symmetric. However, nice, it is almost orthogonal. So what we did, what we show here is of these 5,000 Fourier vectors that we find, we do the pairwise, 5,000 choose too many angles between them, okay? Pairwise angles between base vectors. And you see a histogram here, and in the histogram, you can see that almost all of them angles are beyond 80 degrees, almost all of them. You see nothing here just because the values are so small. I mean, it's 25, a histogram of 25, no, like 12 million angles or so. So it's almost orthogonal, meaning it's also nice and numerically stable, because again, the Fourier basis, you need to invert to get the Fourier transform. And the inversion is only done if it's numerically stable, meaning a good condition number. Okay, so that's the story. So what do you do with it? Well, if you have an application and that application needs a Fourier basis, you can just use that. Fix the graph, get the Fourier basis, and apply your method, and then you can see how it works. And we did some examples in the paper, and it worked very well. I also want to say the same method works if you prefer the Laplacian. Also for the Laplacian, you can fix the graph. And just to make sure really how well it works, we picked some simple examples in the paper, but then later in this paper, I asked one of my students to really do something more sophisticated. Here's a very sophisticated graph denoising method that is based on unrolling an optimization algorithm into a neural network that is then trained. The key is this method needs a shift and a Fourier basis, which for digraphs, directed graphs, you don't have. So we did our approach. And then we tried here in the paper all kinds of combinations of shifts and Fourier basis that people have proposed in the literature, others. And it turns out it works well. Okay. So what I'm saying is we really looked at it very seriously that we get something meaningful. Okay, that was a part 1. Okay, so it's a method. If you now like to work with directed graphs, you need a basis. You can use this. The code can be downloaded. It works. We make sure of it. Otherwise, send an email. But it should work. We really paid some attention because I don't like irreproducible research. So, okay, but now let's come to something else entirely, even though it's also about directions, and we will end up talking about graphs. But here's something novel. And the story starts sort of in the year 2016. So I had just been department head for 3 years. I got a sabbatical, and I thought it would be nice to work on something again, sort of in postdoc mode, right? So just me in my office, of course, supervising the students, but doing something myself, okay? And I was wondering, what should I do? Obviously, the GSP train I had missed, so what am I going to do? And I stumbled across this paper. So this paper is from STOCK. That's the main conference in theoretical computer science, not signal processing. And I saw this equation. And this is about set functions. That is, if in our terms, a signal whose signal domain is a power set. And this looks very much like a convolution, right? I mean, this is a set minus, right? So if you put a minus there, it totally looks like a convolution. And I thought, wow, this is really interesting. I have never seen something like this. So I read the paper and the other papers of the people. They had completely different applications. There was no mention of Fourier transform and frequencies. So of course, with this algebraic work in the background, I was thinking, oh my God, what's the shift? What's the Fourier transform? What's the frequency response? What can I apply? What can I do with it? So I was fascinated and I got to work. And it took a little bit. It was just myself. I was a bit out of training, maybe I was doing math myself on paper. But I just want to sketch to you what came out of it. So let's first do some definitions. So defining the signal domain. You have a finite set with n elements, and then you take the power set that has 2 to the n. It's huge. And now a set function is, that's how they call it, is a signal with the power set as index domain. So every subset is mapped to a number, okay? The index domain is not a graph, it's a power set, okay? And it turns out that in signal processing has not been used much. In machine learning, it's all over the place. Set functions are really relevant, in particular in recommender systems, online auctions, etc. Why? Because maybe you have a bunch of goods and the customer gives some value, these 3 goods together, and then immediately you have a set function, okay? So it has many applications, and people, of course, the trick is how to handle this gigantic size, right? If you have a base set of 100 things, it's 2 to 100, it's enormous. Okay, so after working a bit, it turns out that one very natural way of defining a shift is like the equivalent of a time shift. Here, it's you, in time shift, you do Sn goes to Sn minus 1, right? You delay by 1. And here you delay by subtracting 1 element. Okay, so you see here, this is, if you think this is a set minus, put a minus there, you subtract 1 element. Very natural. It looks like it's a delay by 1 element. You could call it like this. But it's tricky, right? This one is not invertible. And you have now n shifts, n. For every element, there's a shift, right? And every element you can subtract. And that, of course, got me interested because before, remember, 1 shift is graph signal processing. So here, maybe we are up to something new, okay? Because we have n shifts. You can visualize this. The power set can be visualized as a hypercube. Here you see for 3 elements. So on the bottom is the empty set. On the top is the full set. And then you have edges between sets that only differ by 1 element. And here's sort of a visualization of the shift on the equivalent of the Z transform, which we defined. Okay. Good. So now I just wrote down the shift. Before I claimed from algebraic signal processing, once you wrote down the shift, everything else follows. And of course, that has to be true also here in this case. So by mechanic work, which still was a bit of work, here's our shift. So what's the convolution? The convolution is this one. It's a bit different what I showed before. It's the sum over all subsets. And look how this again looks like a convolution, right? Just put the set minus to the minus. It looks very much like a convolution. This convolution is shift invariant because all the shifts commute. Subtracting, no matter in what order, is commutative. So we have shift invariant convolution. The Fourier basis you just do by doing an eigendecomposition of the convolution operators or equivalently of all shifts. These are based off linear algebra. And the basis is not particularly exciting, complicated. If I write it in the columns of a matrix, it gets this Kronecker product structure. So it's a matrix that has 1s and minus 1s. And then the Fourier transform I get by inverting the Fourier basis, as always. And this is self-inverse. So the Fourier transform matrix shown here is the same one. And if you want, like, prefer in closed form, it has this funky form. The Fourier transform at index B is just this sum of the signal values. So it looks very combinatorial, and it's in fact a very combinatorial object, okay? So this is as usual the Fourier transform. Also note that the spectrum is again a set function. So the spectrum is again a hypercube. Turns out, I mean, one has to, of course, develop all these things and look at the math here just to get you maybe a little bit interested. And as always, the Fourier transform diagonalizes all shifts and filters. So you get in the frequency domain, you have a frequency response, which is computed differently from the Fourier transforms. You see it here. And then you have a convolution domain. Convolution on set functions gives you pointwise multiplication in the frequency domain. All this algebraic signal processing just follows linear algebra. Okay. So that's cute. So we have all the objects. So now you, of course, start to think, what can I do with it? But before I want to tell you, there are actually variants. So in fact, by working on this, I found there are 4 variants of doing shifts, and they're all closely related. And I show them here in the top 4 rows. So don't worry about the details. but because the shift's not invertible, you can do different things, slightly different. Instead of subtracting an element, you can add an element, for example, right? And you get variations. And on the bottom, on the row number 5, you see the classical Fourier transform for set functions, which turns out to be a good old friend, which is the Walsh-Hadamard transform, which has many interpretations. And one is Fourier transform for a set function. So this is what people have used in machine learning before. And the shift that goes with the Walsh-Hadamard transform is the symmetric difference. Here you see it. You see, it doesn't look as natural as the shift where you just subtract one element. But the nice thing is, if you visualize it, it's undirected, and that's why the Walsh-Hadamard transform becomes orthogonal, which of course is very nice. Ours, not orthogonal. Okay, not orthogonal. Good. So that's what we had. Now, the one question, of course, is what does that mean, right? For example, the spectrum that I get, what does this mean, right? How do I interpret? And that took a little bit of thinking. And it has a meaning, and it's neat, arguably. And I want to explain this here. What's the meaning of the spectrum when I compute it? So imagine you have sets of goods. So here I show a laptop, a tablet, and a pen, the pen that goes with the tablet, okay? So that's my ground set. It has 3 elements. So my power set is 8 many. And now for a particular customer, every subset of these has a value to me. And that gives a set function, right? Because every subset I give a value. So for example, let's say that the tablet has a value of 2 for me, and the pen of 1, and the laptop of 2. It gets interesting now if I look at larger subsets. So for example, the value of the tablet and the pen together may be more than the sum of the individual values because they have some synergy. And the people in ML, machine learning, they call this complementarity. So the value may be 4 and not 3, right? Because they do something together that is a synergy. You could call this a synergy. On the other hand, the value of the tablet and the laptop together could be still 2 because I can do the same things with them. I can, if I only want to check emails and read news, then adding the laptop and I have already the tablet is nothing. So the value may be smaller than the sum, and this is called substitutability. And you can imagine if I now have larger and larger sets, these interactions become more complicated. Now, once I have all these values for me, I can create a Venn diagram with weights. And to read this is here I have the tablet left here. The circle that goes with this tablet has the weight of the value. So you see here 3 numbers in the circle, 2, 1, -1. If I add them up, I get 2, which is the value of the tablet. The laptop has this circle. If I add up all these values in there as a 2, that's the value of the laptop. And for example, if I take now the value of the pen with the tablet, this is this here, I add this up, 4, 1, -1 gives me 4, okay? But there's a bit of work involved in getting these single values. It turns out these values here, they capture the interactions, right? Negative means complementarity, positive means substitutability, etc. And it turns out that's the spectrum. The spectrum captures these interactions in the value. So that's the spectrum, okay? So, which is interesting. So the Fourier transform, visually speaking, it computes the weights of the fragments from the weights of the subsets of the values. And there's a notion of low and high frequency. The higher order interactions, they are high frequencies, the lower order are low frequencies. And the spectrum is also a set function, okay? So it's nice, you have the structure of the spectrum immediately. So the spectrum that we saw before, here the spectrum has only 4 non-zero values, so it's Fourier sparse because these values here are 0. Okay, and you could imagine that Fourier sparse makes kind of sense, right? Because at one point the values should become additive in a sense. So for example, imagine a situation where the value of a subset is just the sum of the values of the individual items. That would be this situation. The circles do not intersect. There's no interaction. It's just the sum. This would be a super low frequency signal. Okay, it would be a frequency band only 0, 1. Okay, so you see it has an interpretation that actually makes sense. Okay, good. So we have an interpretation. We have all the transforms, frequency response. So what do we do with it? So we considered a few applications, and in particular, the Fourier sparsity I tried to show here makes sense, right? Fourier spars makes sense because that you have arbitrary higher order interactions is unlikely. At one point, the value of sets will just be composed by sums. And there's one actually sort of really interesting application is auctions, iterative online auctions, where you have bidders. And for example, spectrum, right? The radio spectrum is auctioned. We're talking about billions, and there are researchers on auctions. And every bidder has a particular set function attached, which is the value that they give to subsets of the spectrum. So for example, here are these boxes here are spectrum bands that are being auctioned. And maybe the first bidder gives to these 5 red ones gives a value of $150. Of course, in reality, it would be more like 150 million maybe. And the other gives 500. And if I choose a different subset, then there's a different value, etc. Now, if you have 20 such licenses, of course, you're not going to ask the bidders to give you 2 to 20 many values. But you need to have some information on the bidders to run the auction efficiently, because it's about a lot of money. And an auction, such an auction typically starts with something called preference elicitation. What they mean is they ask bidders, give me for these subsets your values, a small like 500, and then they try to estimate the whole set functions, okay? And typically 500. And now we had, of course, natural, with what I've shown before, the idea, let's use Fourier sparsity. Let's make the assumption of that it's Fourier sparse and use that dimensionality reduction to estimate the set functions from few samples, okay? Just like we have done in normal signal processing. If you know it's Fourier sparse, there are famous algorithms, FFT for Fourier sparsity, MIT, etc., that can do that. Of course, now we need first the algorithm and then apply it. So we assume bidder Fourier sparsity. Now, to work in this domain, you actually don't work with real-world bidders, you work with models. The first sanity check was, let's do a model instantiated for 20 licenses. So you have 2 to 20 subsets. And the model gives you these values on the left. That's 1 million values. We compute the spectrum with our Fourier transform. It turns out it's super sparse. Okay, so indeed, the sparsity assumption is not nonsense, at least. And then my student Chris developed an algorithm of computing the Fourier transform under the assumption of Fourier sparsity with unknown support. So similar to the celebrated MIT algorithm for the FFT from a while ago. And it works quite well. And I just want to briefly here's some bidder types. Here's the reconstruction error. You see our work, he gives good reconstruction with only, let's say, number of queries, meaning, let's say here, 70,000 queries, so 70,000 samples. Now you will say this is a lot, and it is. However, the ground set is 98, so the set function has a dimension of 2 to 98, and with 70,000 reconstructing it quite well is very good. Unfortunately, if you go to auction people and say, hey, we can reconstruct the bidder perfectly with 70,000 queries, they say like completely irrelevant because you cannot ask more than 500. But then actually we found in our neighbor university some auction people, and we worked a bit more on it and with some machine learning trickery, and came up with a new form of auction based on Fourier sparsity, which was neat because in this domain, the word Fourier had never appeared before. Okay, so that's neat. So we have now signal processing on power sets. There are several shifts, so that's interesting. The transform itself is not so super powerful, but at least here's an example of what you can really do with it. Okay, so me in my postdoc mode, I was happy and thought, okay, that's it. However, it turned out that we can actually generalize this. Okay, so it turns out this convolution I just showed, which is here on the top, the set difference with A can be written as an intersection with a complement of A. That's the same thing. And by a little base change, instead of using the complements, you can get A directly, and this is kind of an isomorphic way of writing this convolution. And it turns out this is a special case of something more general, namely the power set is a so-called meet lattice, okay? And the meet operation is the intersection. So here you see on the right, the meat is now written like this. It's something more general. I will explain in a second, but the generalization is straightforward. If you have a meat lattice, just plug in that thing here. And now you have again something that very much looks like a convolution and now works for all meat lattices. Okay, so what are now these meat lattices? I mean, it's fundamental in computer science. We teach it in the first semester actually to all students. So of course I had also learned this once, but of course didn't know too much about it. So get a book on lattice theory. Here's a standard book. Imagine 640 pages of lattice theory. So there's some chunky theory going on. And look for the Fourier transform convolution. Is nothing in there. There's no convolution in there, no Fourier transform, despite 640 pages. So I thought, great, more postdoc work to do. Let's figure this out sort of by myself. I looked at related work, and the only thing I found is this here. This is again the Scandinavian team that wrote also the prior paper that got me interested into this. Okay. So let's talk about this meat lattice. So a lattice has two properties. It's a finite set again. Here I use finite set, and it has a partial order. Okay, so the elements are ordered, but not total. Not all elements are comparable. Okay, so it's just a partial order. And it has these axioms. So there's transitivity and so forth. So it's a partial order. Okay. There's an additional property. When I have two elements, there is a unique maximal element, a unique element that is smaller than the two and maximal. Okay. Okay, so math is hard to digest always. So let's look at examples. A lattice is typically a partial order. You write them as a graph. So we are back in graphs here. You write them typically as a graph. The small elements on the bottom, the large elements higher up. Okay. It's naturally directed because it's an order, right? You know what's smaller and larger. So this thing has directions. For example, this here is a lattice. Okay. So for example, if I pick E and F, there's a unique maximal element smaller than both, namely B. And E and G, the meat of the two is A. Okay. This is the total order. Everything is comparable. That's the hypercube, which we had before, is a lattice. This is not a lattice. And the butterfly here, so to speak, kills it. Because D and E have B and C smaller, and both are maximal smaller, and you can only have two. So that's not a lattice. Okay. So there's no unique meat operation. That's forbidden. So in other words, the lattices are a subset of directed acyclic graphs. The total order makes this a directed graph. It's acyclic. There's no cycles. And but you need to have some additional structure so it makes a lattice. Not every DEG is a lattice. Good. Now again, the shift I wrote already down. Here's a lattice signal. There's the lattice, finite set. Every element you get a value. And here's the shift that I said before, because the meat is everything you have. Let's just use this to shift. Again, you can call this a delay because it makes the index smaller, right? If you do the meat, you make it smaller. So it's kind of a delay on the lattice, which is kind of neat. And again, you have many shifts, but again, they all commute. So we get shift invariance. That's nice. Again, algebraic signal processing claims once you have the shift, just derive the rest. And the convolution, not surprisingly, looks like this. The Fourier basis, you can just derive, and that gives you the inverse Fourier transform. And the inverse Fourier transform looks like this. So the signal value is a sum over spectral values over all predecessors. And here you have the partial order. And the Fourier basis has only 0, 1 vectors. So again, only 0, 1 vectors, very combinatorial. And it turns out this thing, to invert it, to get the Fourier transform, you get classical, here, classical seminal paper from combinatorics from '64. And that tells you how to invert this with called the Möbius function. This is called the Möbius transform, and this becomes now the Fourier transform. So you see here, this is a frequency, a spectral value. Here, the signal values. You sum over all predecessors with some weights that are computed like this. So that's how it works. And again, the Fourier transform diagonalizes all shifts and filters, etc., etc. So we have the full set of constructs. Okay, good. Here's an example. We played a bit around with it and developed some applications, and you can look at it in the paper. Okay. Now, the lattice is a bit an exotic thing, you may say, and it is, but it exists. Okay, there are applications. In particular, there's a very interesting connections to hypergraphs. Every hypergraph can be described by a lattice, which I didn't know before. So you can look at the paper, and I think there's more work that can be done. Still, it's a little bit exotic. The Fourier basis is only zeros and ones, so you can argue, is that so interesting? I don't know. More work needed. I want to point out something, though. One of my students worked on getting a fast algorithm for that Fourier transform we just derived, which in the literature only existed in special cases. And he found a very neat algorithm. And I just want to say that if the DAG, the directed acyclic graph that describes the lattice, is sufficiently sparse, you can go to 10 million. Okay. So that's really neat. So in other words, even if you say, oh, this is maybe not so powerful, if you have a lattice, at least you can go to 10 million. And that's something interesting. And also that code is downloadable and so forth. So in fact, that also motivates me to look more into this, because 10 million in graph signal processing is out of reach. Okay. Okay, so done were the lattices, and now we had some new forms of signal processing, a little bit exotic, but mathematically neat with interpretations. In the papers, we have more things. And kind of we thought we are done. But we were not, and now it gets interesting, and back to the topic of graphs very much. This is what I showed before. Here's the lattice convolution. Here's the inverse Fourier transform. Here's the Fourier transform. And sort of a neat insight I want to really attribute to Chris, who went with me through all these versions and helping to find applications, etc. He looked at this one day and he said, look, if I look at this Fourier transform, at this inverse Fourier transform, there is this partial order here, but nowhere is there a meet operation. There's no meet operation here. So do we need that meet, or can we just drop this property of this meet and we get all DAGs? Okay. And while we are at it, why not add weights also? Because there's no weights on the graph. So far, the graphs were unweighted, and we know weights are really important in applications. So could we have something that works for all DAGs and the edges have weights? And the question is then, but how do you do the shift then? Because the meet is gone, right? So how do you do a shift if you only have a partial order, if you only have a DAG? And again, I want to remind you, we saw a DAG before, that path graph. DAGs are the worst case in GSP, right? The adjacency matrix looks like this. If you order the vertices in the proper way, it looks like this. The eigenvalue is only 0, it's one Jordan block, there's no basis whatsoever. Okay, so interesting, because they're also highly relevant. The entire literature on Bayesian reasoning is based on DAGs. Everything that is causal is driven by DAGs. So in machine learning, there's a whole area on causal inference, and it works only with DAGs, because any causal sequence of events is a DAG. Good. Just a sanity check. I want to stick with the time. We started a bit late. I have 10 minutes for sure, right? Okay. Good. I like to stay on time, so. Okay, but this is good. We have enough time. So let's talk about DAGs and this partial order. Before I talked about partial order, but we visualize them as DAGs. Now let's talk about DAGs. DAG, directed acyclic graph. Okay, so first, if you have a DAG, it defines uniquely a partial order. Okay, because if you have two nodes in the DAG, and one comes before the others, you say it's smaller. And if not one comes before the other, then they are not comparable. So it gives you a unique partial order. Okay. Here's the definition. A is smaller than B if and only if A is a predecessor of B in the DAG. Okay, like an ancestor. Conversely, is a bit more tricky. Any partial order can be represented by multiple DAGs because of transitive edges. So let me show this here. All these DAGs give the same partial order. All these DAGs give the same partial order. This one here is the one with the minimal number of edges to present a partial order. And then this one adds here this edge. But you see, this edge doesn't do anything to the happens before relationship, right? So it's a transitive edge, right? It can be transitively decomposed into two edges, so it doesn't do anything. So same partial order. And you take this to the extreme and you do the transitive closure and it gives you still the same one, okay? So in essence, this is the neatest representation. It's the transitive reduction, but any one defines the same partial order. So it's not one-to-one, okay? But still, they're very closely related. Okay, so now let's try to build our signal model in the algebraic sense, meaning we want our shift, we want our convolution, we want the whole thing by generalizing what I showed you before. Okay, so now we start with, given a weighted DEG, so we add the weights. Here's the DEG, can have a transitive edge, that's fine. And we have weights on all the edges. And the signal on the DEG, like in graph signal processing, attaches to every node a value, okay? Just like in GSP, same idea. And now what we assume that the signal is a weighted linear combination of values from all predecessors, okay? So you take at value at point X, all predecessors, and they have associated with values C, Y, and then there are the weights then there are weights. So that's the assumption. And the signal value is what you observe. These C values are unknown values. You assume each node produces such an unknown value, and the observed signal value is a linear combination, so it's a linear model. And we call them causes because if S is computed from the C's, it looks like causal. However, then we started to look into causal inference. Causal inference is tricky. If something is related to something else, doesn't mean there's a causal relationship, right? So you can have confounding variables, and you need to do much more to really establish causality, right? So this is an active area of research. But let's say here, we just call it cause and slight abuse of notation, because S is computed from the C's. But there's more that needs to be done to do real causality. It's a difficult topic. The W are weights. And you know, what I show you here looks very much, okay, the weights is the question, how do we get actually the weights? Because I sum over all predecessors, but the weights from the graph are only from the edges, okay? So they don't give me weights for all predecessors. And this here is in essence like the inverse Fourier transform I showed before. I sum over all predecessors with weights. So this will be my inverse Fourier transform with the causes being the spectrum, okay? And that generalizes what we saw before on the lattice. Now let's try to get a bit more intuition on this. So here is on the left what I showed before. S is observed, C is unknown, and W will be my inverse Fourier transform. But W is not specified by the adjacency matrix because I need values for all predecessors. And here's sort of an example that tries to get a mental model what that could look like. Imagine that weighted graph here is a river network. The nodes are cities, and every city inserts some pollution into the river, and you don't know which one, okay? And the edges tell you how the pollution is divided as it moves along. So for example, from this city, 30% of the pollution goes to city C and 70% to city D, okay? And you don't know what the cities pollute. And what you observe though, at every node, you observe the pollution by measurement. So you measure at each city, you measure the pollution, but the pollution that you measure is of course the aggregated pollution for all predecessors, okay? And the question is, how do you compute this aggregated pollution? And it turns out in this case that W, which relates the inserted pollution to the measured solution, is given by this. So you take the adjacency matrix and you power it up, okay? It's relatively easy to understand. That W computes the measured solution in the river from the inserted pollution at all cities. And this is a form of transitive closure. Actually, it's a form of transitive closure on the graph. So in this case, that transitive closure gives you sort of the weights here for the pollution contribution for all ancestors. And that means in this case, the Fourier transform would be this. So this here, this transform computes from the measured pollution, the cities, and how much they inserted in pollution. So that's one model. So in that model, we had a particular transitive closure. It turns out there's a theory of transitive closures, and you can have many different kinds of transitive closures depending on the meaning of the weights. Here it was fraction of pollution. If the weights mean length of a path, you do the transitive closure with the shortest path computation. If it's throughput, then you have another one. If it's influence, you use another one. And so there are many transitive closures that make sense depending on the meaning of the weights. And that gives you then different Fourier transform for the particular model. Okay, and so we imported that theory of transitive closures, and they all can be computed in cubic time using some version of Floyd-Warshall. Okay, so what about the shift now? I didn't talk about the shift. I immediately wrote down the Fourier transform, which looks like this. Here's the inverse Fourier transform signal spectrum. There's a chosen transitive closure. That is the Fourier transform. It turns out the shift is now a bit tricky and best understood in the frequency domain. So here I have the frequency representation of a signal. And if I take this signal, this is frequency domain, right? Here's the spectrum. If I shift by a value in my DEG, by a node, Q, what I do is I just change the sum like this. So it's the sum over the common causes of X and Y. Okay, and this is a pointwise multiplication in the frequency domain by 0 or 1. So it is diagonal in the frequency domain. Okay, good. Maybe let's here's a visualization, maybe in interest of time, because I have 2-3 more slides I want to really mention. So there is a notion of shift, but without that, thinking is actually at first non-intuitive. In the frequency domain, it makes a lot of sense. And it generalizes what we saw before. Okay, so now the question is, what do we do with this now? So we have now a Fourier analysis on DEGAS. There's no cyclic condition, anything. It is causal in a sense, because it only works with the partial order. The effect is all the Fourier transform shifts are all triangular, okay, triangular, not orthogonal. Now, there's this neat interpretation now in this model. Fourier sparsity means a signal has few causes. That's neat, that's understandable. So naturally, again, we jumped on this. And in the paper, we show an example where we learn a DEGAS signal under the assumption of Fourier sparsity, just like we did before, and it works quite well. Okay, because Fourier sparsity makes sense. But recently, and this is now work from the last 2 months, we got into actually something arguably more interesting, namely learning the DEG. Okay, so imagine you have data and you want to learn the DEG. We saw yesterday many talks actually about learning the graph from data. Now let's put here our theory to use. Learn the DEG from data. This is an active problem in machine learning because it is sort of causal inference, right? What causes what and so forth. So learn the DEG from data under the assumption of Fourier sparsity, okay? So the question is, have people done this? And it turns out no, and that was kind of novel. So people use for causal inference, they work with these structural causal models, and there's a linear version closest to our work. It looks like this. And in essence, what this means, a value at a node is a linear combination of the parents plus noise. And if you turn this into our language, it's like the noise is the spectrum of the signal in this case, the noise, and it's typically IID Gaussian. So what we did is, this is what people typically do. In our language, the spectrum is IID Gaussian noise. We changed this to Fourier sparsity. So we said, no. We want a spectrum that's Fourier sparse plus a bit of noise. And we also add measurement noise, thinking about the pollution example. And okay, that's the model. How do you learn the DEG from this model? That's straightforward, leveraging prior work. This is the optimization problem you have to solve. You have a lot of data, let's say 1,000 samples on the DEG. And this term, as you see, is a 1 norm. It's a relaxation of the 0 norm, enforces a sparse spectrum. This one enforces a sparse DEG. And this one, that's a beautiful trick from this paper, enforces it's a DEG. It enforces acyclicity. So that was actually a cute thing. This term enforces you learn a DEG that is acyclic, which is at first glance non-intuitive how to enforce this, okay? So we ran this endless tables against all the other methods that are out there. under the assumption of Fourier sparsity. I want to point out this table because I was very happy about this one, where we really scale it up to a few thousand nodes with many edges. And these are here the fiercest competitors. And it turns out in this metric where lower is better, we learn the DAG perfectly, including the weights. So that was a really nice success with 5% sparsity. If you have less sparsity, smaller, also looks good. And some caveats, but it works really well. Yeah. Okay, so that got us excited. This is all on arXiv, submitted and so forth. And the last thing which happened 2 weeks ago, my student who worked on this Panos, he found a competition of some pharma company. They invited people to submit their algorithm to do causal inference on gene interaction data. And they gave some data to play and to make it compatible. But then in the competition, they took the algorithm and ran it on their data in-house that you didn't get to see. And we made the 3rd place, so the student was delighted, and we couldn't believe it. We were the only one that came with this Fourier sparsity, the other had other algorithms. So in essence, what this means is that Fourier sparsity at least can make sense in this domain, and more research is needed. So we got really excited because this is true real-world data from that company, and they there were some nice things about it, that they will actually look further into this few causes assumption that this really works. Okay, so this gives us, that's the end of the story, and this is all ongoing work, and we are all excited, and hopefully more things come about. Okay, let me conclude. I had 2 parts. The first was a solution to get Fourier basis for digraphs, adding 2 prior solutions. You can judge which one you like best. What I like about it, it generalizes what we do all the time in discrete time signal processing, and it works, it's scalable, but I invite you to try it out, whether it really works in an application that you care about. And then this new exciting research that started with me going back being a postdoc, and then turned out into a lot more work done by my group members that I showed you before in pictures. We started with power sets, got a Fourier framework, then generalized to lattices, and then generalized to arbitrary DAGs. It's something different from GSP. It's on the happens, the shift is on the happens before relationship. So now you can do DAGs or equivalent partial orders with weights. And of course, more work is needed to figure out how much you can do with it. And everything is driven by that earlier work, and everything is multi-shift, so it's really different from graph signal. And that's it. Thank you.
Excellent talk. Time for questions?
I have a comment and 2 questions,
Yeah.
so I'll ask maybe the questions a little later. My one comment was, so with your lattices, since Boolean algebra generates a certain type of lattice, a distributive lattice, I'm wondering if your decompositions would correspond to sort of logic decomposition that you've ever tried to do.
Yeah, I cannot say. I mean, we looked at many kinds of lattices. And of course, to try this out, you need data on the lattice, right? In principle, it works for every lattice, but some lattices are maybe way too big, so you cannot do anything. But then you need data, so on the lattices, right? So, and that's in fact where a lot of the work went to find real cases, right? So we looked at all kinds of lattices. That would be something to look at. I mean, we really, honestly, we spent on this easily close to a year. I mean, not full time on the side. And we looked at all kinds of lattices. The set of partitions is a lattice, right? And so forth. And of course, many of these lattices are very irregular. And of course, where it gets interesting is when you have lattices that are more real world, that are not have an obvious structure. And what I'm most excited about is this thing called concept lattice. We have it in the paper that in essence is a way of representing tables or hypergraphs. And I think there is more work one can do, but even there we struggle to get some data and do something meaningful. So I mean, please look at it if you have an idea. I mean, I'm very happy data and lattice is very happy to look more at it.
One of my questions was just about this method for directed graphs and student as well. Is it basically sort of generalizing this idea of adding cycles to?
Absolutely. And in fact, you can get in the paper we discussed this. If you want to get rid of zero eigenvalues, which we also do in the site, right, it's not good, then you need to get rid of sinks and sources. Every sink and source gives you a zero eigenvalue, right? Because it gives you a zero row or a zero column. So it's exactly, it generalizes in a very nice way. And also we obviously change the characteristic polynomial. And there's a theorem that relates the characteristic polynomial, the coefficients, to the cycles in the graph. So in other words, you can only change the characteristic polynomial by changing the number of cycles in the graph somewhere. So in other words, this really generalizes this thing of we need the cycles. So in fact, it really captures the fact that we need cycles, otherwise this GSP doesn't work. We cannot be pure causal in essence. We need these cycles, and this does it. It makes everything to cycle. Yeah.
Its third question is very vague. I studied gene regulatory networks a little bit, and they are not DEGAS. Genes have a lot of cycles actually. And that's why I was wondering, I heard about this competition, but I was like, the causal graphs are always DEGAS, but do you think that's one of the reasons?
That one was really a DEGAS. So I know that, I mean, really the full-blown gene regulatory networks, they are really digraphs and really directed graphs. They're definitely very directed. And I keep talking to my computer science people to give me some data, and we tried out stuff, which then didn't work, right? But I mean, but that particular competition, I think it was a very particular problem, and they wanted causal inference on DEGAS. So it was really posed as a DEGAS learning problem. And for those who knows causal discovery, it was even with interventions to really prove causality. You need to go into the data and artificially set one value to 0 to make sure it really causes an effect later. And the algorithm we had could be even done with interventions. So that was part of this. So just for those who like causal.
Regarding the first part of the GSP graph, so you mentioned that the Jordan form gives you like all the theory to solve the problem, but then you have this stability and scalability issue. Have you looked at maybe other decompositions that are also valid for like the graph, like the Püschel decomposition, other decomposition NDD? Like I'm trying to maybe
Yeah.
those are more stable. Maybe you can sort of go around the Jordan form.
Yes. We looked at all these. I mean, I'm aware of this decomposition, and there are prior work that used this decomposition. Sure decomposition was used in prior work. I think Jose had a student that worked that had the sure decomposition as. So people have done this, but I wanted to stay as close as possible to the original GSP by really having a Fourier transform that diagonalizes a meaningful adjacency matrix. So I wanted to stay as close as possible to the framework, right? Sort of that's one thing. And of course, we had this idea and it just matches and fits nicely, but maybe you can port it. If you care about another decomposition and that doesn't always exist, you could port the idea potentially, but we didn't.
For the scalability and stability.
Yeah, but we didn't look at it. This was really done to have a solution close by. It works. It is as scalable as you want, because beyond 5,000 you cannot compute much anymore anyway. But maybe you can port it to others that you care about, right? We didn't look into that, and we were happy with that result. Let's say. Let's say also the person wanted them to do something different and worked on the DEGAS, and you have things like this sometimes also. Yeah.
You say you can avoid.
Okay, Markus, wonderful talk. And of course, we have a lot to speak from the next few meetings. Minor comment. Minor comment in the sense that I'm trying to get from you. Why are you concerned, or why do you make a statement like, if I have the Jordan form, I cannot define the Fourier form? Okay.
No, you can. I know you did work where you can use, but you cannot compute it. Right?
This form is to the invariant decomposition.
Yeah.
Right. So okay. Now the other comment is, and this is in Fourier, you define on your later work this signal as being the linear combination of all the past fields.
Of past values that are unknown. Yes. Mm-hmm.
You have x less than or equal to y.
Yeah, pretty safe.
So in signal processing, that's called the wall decomposition, uses all the past. But if you use a Markov property, then you only use a negative, why, what would be the impact on your conclusion if you, and of course, all of you, simply because it's the parents and not the father, what would be the impact on your conclusion?
So when I showed what people did on these linear structural causal models, they do that. They have the Markov property, meaning every value is a linear combination of values from the direct parents, not all predecessors, plus noise, okay, which is very simple to Gauss Markov random field on a DEG in reality, a causal one. And then you can unroll this. That's like a recurrence, right? The signal values depend on prior signal. And when you unroll the recurrence, you get that what I call the plus times transitive closure, which does it in one go, meaning you compute the signal values in one go from all the noise, okay? What we found, and this is something needs further study, how much sense it makes, since this is a transitive closure, that maybe you want to study other notions of transitive closures, where the Markov property then takes sort of a different, less obvious form, okay? And for example, if the weights are distances, then to compute the distances to all predecessors, you would run a Dijkstra's shortest path algorithm, and that would be different from powering up, and you would have a different transitive closure. You could then again put it again into this Markov form, but not with the adjacency, but with some other matrix. So, and this is something we're currently thinking about, but the theory just naturally gave this opportunity to consider something a little bit different, but you can again put it in the Markov form if you want. And that requires a bit more on paper to show why this is. We're currently thinking about this and trying to put this to use. It requires a bit of on paper, right? But in essence, you can still write it then in the Markov form, but then there will not be the adjacency matrix. There will be something else that is defined by the other transitive closure.
One last one.
Yeah.
Could you please show me your slide on the structural equation model where you have the part with the no one?
Yes.
So I was expecting there to have like my question is, can you do a least square like the signal of the in the node minus the metric matrix times the signal in the node again? I was kind of
So you want sorry, where is it? Here.
which is
You want to change one of these terms to the 2 norm, is that it?
yeah the first one. What is the first term, the first
Mhm.
L1 norm?
So we put a norm because what we want is that if I take my data, the observed data, and apply the Fourier transform to get the spectrum, that this is sparse. So this would be S times W inverse. W is the inverse Fourier transform, W inverse the Fourier transform, 0 norm. And then as common, when you have a 0 norm, you relax it to the 1 norm. That's the motivation. But you can study other variants. And but here we wanted sparsity in the Fourier domain, and that wants the 1 norm. It's a relaxation of a 0 norm.
Not only on the adjacent matrix, but on
Yeah.
the part.
Yeah.
That's how we
Exactly.
have it.
Exactly.
That's all for this session.